Hello everyone, my name is Shubhanshu Shekhar, and I'll be talking about her work, Instance-Dependent Regret Analysis of Kernelized Bandits, written jointly with Professor Tara Javedi of UCSD. So we consider the problem of optimizing an unknown objective function f that maps the unit cube in d dimensions to the real line. We assume that the function f can only be accessed via a noisy zeroth-order oracle. As shown in the figure, the noisy zeroth-order oracle takes in any point x in the domain of the function f and returns the function value at that point plus an additive noise term. To make the problem tractable, we make the following two assumptions. First, we assume that the function f lies in the reproducing kernel Hilbert space associated with a given kernel k, and its norm is upper bounded by a term m. Second, we assume that the noise is drawn IID from a zero-mean Gaussian distribution with a known variance sigma squared. Within this framework, and given a total querying budget n, our goal is to design an adaptive querying strategy to select the points x1 through xn such that the total cumulative regret incurred by that strategy is small. Prior results in the literature have mainly studied this problem in a minimax framework, and in particular, for the case of Mattern family of kernels that is considered in our paper, Scarlett et al. Showed that the worst case expected regret of any algorithm must satisfy the following lower bound. Additionally, there exist several algorithms in literature with strong theoretical guarantees of the regret, and some of them are even known to be minimax near optimal, as shown in this table. However, the existing results suffer from the following two drawbacks. First, the min-max lower bounds, due to their worst-case nature, provide limited information about the performance of commonly used good algorithms on typical non-adversarial problem instances. And second, the existing regret upper bounds do not have the ability to adapt to easier problem instances in the function class. That is, they imply the same bounds for all problems in the entire function class. Our results in this paper take steps to address both these issues. In particular, we first derive instance-dependent lower bounds on the regret of any algorithm that achieves uniformly good regret over the entire function class. We then propose an algorithm that can provably adapt to some easier problem instances and achieves faster than min-max rate on those problems. To state our instance-dependent lower bounds, we need two assumptions. The first assumption requires the expected regret of the algorithm A to be smaller than n to the A0 uniformly over the entire function class. The second assumption requires the function f to satisfy a polynomial growth condition in the neighborhood of its optimizer. Under these two assumptions, we show that the expected regret incurred by the algorithm A on problem f must at least be of the order n to the alpha, as shown here, and the term alpha depends on the uniform regret parameter A0, the smoothness parameter nu, the dimension d, and the local growth rate b. Furthermore, we know that alpha increases with increasing values of A0 and b. This means that instance-dependent lower bound is larger for algorithms with stronger uniform regret guarantees and on problem instances with flatter near-optimal regions. For our next result, we design an algorithm A1 for which the expected regret is of the order n to the alpha with the term alpha as shown here. This result implies that the worst-case regret of a proposed algorithm matches the min-max rate, showing its min-max near optimality, and furthermore, for certain ranges of the smoothness parameter nu and the growth rate b, the expected regret of our algorithm is strictly faster than the min-max rate. So the two figures compare the upper and lower bounds for several commonly used algorithms in kernelized bandits literature. The dashed curves show the regret upper bounds of the different algorithms, while the corresponding solid curves of the same color represent our instance-dependent lower bounds for those algorithms. As indicated by the figures, there's often a large gap between the upper and lower bounds, and an important question for future work is to develop new analysis techniques for closing this gap. Thank you.